So, okay. So we'll be talking about dynamic programming on tree-like graphs. Let's just start with some introductory warm-up till people join. So let's just start with some warm-up. So first question: what is dynamic programming in general? And we all have seen dynamic programming in various courses before. So the basic idea of dynamic programming is you have an optimization problem. And what you'll do is you'll break this optimization problem into smaller similar optimization problems or sub-problems. And then using the solutions of these sub-problems, you will find a relation to the solution of the actual problem. And this is basically a very good technique because it helps us to, do stuff very fast and efficient. So let's look at a very simple example that we saw in our algorithms class. Finding the maximum independent set in a tree T. So you are given a tree, let's call this tree T, and this tree can be rooted. Let's say it is rooted at this vertex R. Then now what you want to find out is the size of the maximum possible independent set in this entire graph. To do so, consider the function a of v. So a of v is basically the size of the maximum independent set of a subtree which hangs at v. So for example, if this was the vertex v, then this entire graph would be your subtree hanging at v, and the size of the maximum independent set in this subtree would indeed be the value of a of v. Now, the original problem is to find a of r because the subtree rooted at r is the entire graph that we want to. To do so, what we are doing is we are dividing it into sub-problems a of v for every v in the vertex of t. And you just keep on finding these values for every vertex until you ultimately reach the vertex r, and then you find the value there. Well, okay, so what is the method in general? So if v is a leaf, then av is simply 1. If v is not a leaf, then you have this relation. Okay, so basically then you'll do this thing, and then in order to do this algorithmically, you run a BSS on this tree. So after running a BSS, you'll get some numbering of the vertices in some order. So this will be first, second, third, fourth, fifth, sixth, seventh, blah, blah, blah. And then you just reverse this order. So after you reverse this order, the first vertex will be here. So first, second, third, fourth, fifth, sixth, seventh, eighth, and so on, and it will go up and up and above. So the children will basically be calculated before the parents are calculated. So you run a BFS tree, you number the vertices based on the decreasing discovery times, and then visit the vertices as per this numbering, calculating a of v at each step. Ultimately, you'll reach R where you find a of R, and this can be done in linear time. So, a simple question: why did dynamic programming help us here? So the main thing is.
I have a question. What is BFS? I haven't taken algorithms.
Oh, sorry. So, okay, fine. If you haven't taken algorithm, then for the time being, we'll just say BFS is a technique of numbering the vertices. So ultimately, after doing this step, I'll get a numbering of vertices which goes from down to up in this tree.
Oh, okay.
So
what's the full form of the?
It's a breadth first search.
I see. Thank you.
So the simple question is, okay, why DP? Why dynamic programming? So dynamic programming is helpful because maximum independent set is actually a NP complete problem. And when I did this problem on trees, what happened is that this became a linear problem. And because of this, what you are able to see is that many NP complete problems can now be solved in polynomial time on trees. So we did this on trees. Then the next question arises, okay, why trees? So again, the reason as to why we are doing this on trees is because if I consider a tree, and then if I look here and then I look at the graph that is hanging from this vertex here, then that is also a subtree, and this subtree is also a tree basically. So every sub-problem has the same structure as the original problem. And this similarity in structures is helping us find a single algorithm which will work throughout. And the second important reason is you are able to easily navigate on these trees. So you know that you can go from children to parents. And there is no weird stuff happening, as in there are cycles or something which can really complicate matters. So that's why dynamic programming on trees is very efficient. But then there is obviously a problem. Like while it is efficient, it is also useless in some sense. Why is it useless? I'll tell you that. Dynamic programming on trees is useless because one, there are very few trees as compared to the number of graphs. So if I pick suppose n vertices, then the total possible graphs on it and the total number of trees, the number of trees are really very less as compared to the possible number of graphs. And secondly, many problems are really meaningless to be solved on trees. Now these problems are really important, but on trees they really don't have any value. For example, is G 3 colorable? So for a tree, you know that it is 3 colorable. It is 3 colorable. It is 2 colorable. Then there is a question as in, okay, you can ask whether given a graph, is there a cycle? You know trees don't have cycles. Is there a Hamiltonian path? You know the answers to this. A tree has a Hamiltonian path if and only if it is a path, like it is literally a path, or it has only 2 leaf nodes. Or finding the maximum clique size. You know that the maximum clique size in a tree is K2 because K3 is a cycle. So while these problems are really important NP hard problems whose polynomial solutions we wish to find, dynamic programming can't help there because these problems are meaningless on trees, and these two properties here that really help in dynamical programming are not seen in many graphs other than trees. Okay, there are planar graphs which we can discuss after the talk, but in general trees are not helpful in that. But the structure of tree is very good and we really want to use the structure in some way for dynamic programming. So the ultimate aim is to generalize the tree. That is, you want to find graphs which look like tree. So how to do this? So this is the concept of tree decomposition and tree sets. Now this concept was given by Hallen first and then Robertson and Seymour, and these two people are really big people in this entire field of graph theory. So they have been working on they have worked on some thing called graph minors and the minor theory, which is also very important, but in general, well, these are really big people in graph theory. So they developed this idea of tree decompositions and tree widths, and we'll just have a look at all of this. So now remember what a tree is. A tree is simply a connected acyclic graph. What does this property like? What is the key feature of a tree? Because it is a connected acyclic graph, what happens is that it is made up of one component, but if I remove any vertex or if I remove any edge, then the graph will become disconnected into some number of parts. We don't know how many, but it will simply get disconnected. This property of separation, that removing any node from the tree disconnects the graph, is what is really crucial in giving trees its structure. Why is this crucial? Because of this separation property, then you can say that, okay, there are no cycles. And if there are no cycles, then basically then you have a unique path between any two vertices, and that will give you a really good structure from going from one vertex to another. So if you think deep about it, this property, the separator property, is the most important property that defines a tree, and the fact that it is connected. So we want to take a graph and we want to make it look like a tree. How do we do this? So first, a simple idea would be, suppose you look at this graph. Okay, so the graph is the one that has been drawn in pencil, the hollow circles in the lines. So if I look at this graph G, in order to make it look like a tree, what I would like to do is I would like to demarcate some zones. So I'll pick some subgraph of this. Suppose I pick this orange one, and then for this orange one, I'll designate a node. Let's say this orange node. For this green one, I'll designate this green node. For this blue one, I'll designate this blue node. And so I will split the graph into these subgraphs. And for each of these subgraphs, I'll present a node here. And then I'll connect this node in the form of a tree. Okay. Now after doing this, there is one more thing that is left is this tree should be formed in such a way such that the separator property holds true with respect to the graph G and not with respect to T. What does this mean? So suppose if I remove this green dot. After removing this green dot, obviously this tree T will get disconnected. That is not an issue. But it could happen that this graph did not get disconnected. And then it no longer functions as a tree, right? So for this graph to function as a tree, I want that when I remove this node here, whatever subgraph gets removed from here should disconnect this graph, right? So this is what I am really willing to find. So step one would be you are given a graph, you split it into subgraphs, not necessarily disjoint, but they should cover the entire graph. Then you form a tree out of these, and you form a tree in such a way that the separator property holds with respect to the original graph G and not only the graph T. Is everything fine till here? Okay. So this is what we'll do. We'll define a tree decomposition as follows. Given a graph GVE, a tree decomposition is a tree T with the vertices I and edges F. So I is said to be the indexing set of this tree. Okay. So vertices are I and edges are F, such that for every node I of the tree, so for every node here, suppose the orange node, the green node, the red node, I am attaching a subset chi I of V to each one of them. So for this green one, I have attached this subset. 1, 2, 3, 4. These 4 nodes have been attached here. And I am doing this for each of these nodes. So then what is the property of all these? The property that this mapping or this attachment should satisfy are these 3 properties. The first one, the union of all these chi i's should be equal to the vertex set. And for every edge U and V, there must be some node such that U and V both lie in that node. This property ensures that every single vertex is contained in some node. This property ensures that every single edge is contained in some node. So together these properties are ensuring that my graph has been actually split properly. Now, okay, once the splitting is done, now the separator property is there. So for separator property, I'll have something like this. What it says is that, okay, I pick a vertex V. And for this vertex, I will look at all the nodes of the tree which contain this vertex. Then this subgraph that I have got, this subgraph should be a subtree of T. It should be a subtree in the sense it should be connected. We'll see some examples so that you'll understand what's happening. So for example, look at this vertex here. So this vertex here lies in the blue one, it lies in the green one, and it lies in the black one. So you look at the subgraph that I have got with this blue, black, and green. So the subgraph is basically this, this, and this. So this indeed is a subtree of this tree. Right? So that is what I want, and I want this to be true for every single vertex in this graph. And this will ultimately lead to the separator property being true. Then now given this tree decomposition, so such a tree that is associated with this graph is called a tree decomposition. Given this tree decomposition, to define the tree width of this tree decomposition as the maximum size of chi i's minus 1. We'll look at this below. So I'll just give you a quick notational preview. So whenever I am referring to vertices of the tree decomposition tree T, I'll call them nodes. And vertices are the vertices of G. And chi I is said to be the bag of vertices which is attached to node I. So I'll look at this example. Have a look at this example, okay? So this is a graph and this is its tree decomposition. Question is, why is this a tree decomposition? So this is your T, and 1, 2, 3, 4, 5, 6. These are the nodes of this tree, and the connected ones are the edges of this tree. Suppose if I pick this node, then the bag associated with this node, the chi for this node, is the set B, D, and E. Okay. Now this is what the chi i's represent. So the chi I over here is A, B, D. The chi for this node is BDE. The chi for this node is BGE. Okay, so why is this tree decomposition? This is a tree decomposition because let's see the first property. First property is that every vertex of graph G should be in some node. So, okay, I have A, B, C, D, E, F, G, and H. So all the vertices are being covered in these chi i's. So all the vertices have been done. Now for edges, what you need to do is, okay, suppose I pick this edge BE. I want to find some node in this tree decomposition which contains both B and E, and there is this node here. Similarly, suppose if I take DE, then again I have this one. If I take, let's say, AD, then I'll get this one, and so on. We can check that every single edge is there inside some of these nodes. Finally, the third condition was the connectedness part. So I have indicated what all nodes contain a vertex. So vertex A is contained in this node. Vertex B is contained in these 4 nodes, and these are forming a subtree. Similarly, C is a single one. D is forming this subtree. E is forming this subtree. F is here. G is here, and so on. This is another tree decomposition here, but we can skip it for the time being. That is fine. Okay, now the question is, what is the tree width of a tree decomposition? So look at this tree decomposition. So this tree decomposition, how many vertices are there in each bag? So the bag here has 3 vertices. The bag here has 4, 3, 2, and 2. You look at the maximum size, that is 4, and then subtract 1. So after you subtract 1, basically you will get 3. So this is a tree decomposition with tree width 3. Okay. And then once you define it for tree decomposition, you define it for a graph G. So the tree width of a graph G is the minimum tree width over all possible tree decompositions. Like I'll draw all possible tree decompositions, find the tree width for each of them, and then find the minimum. In general, these are some results. So G itself is a tree decomposition of itself, which has only one node. This is something very trivial. And this tells me that the tree width is bounded above by n-1. Trees are graphs which have tree width of 1. Like, this is simple to see, so I'll just skip this for the time. And Kn has something which has a tree width of n-1. And this is a very interesting thing. So if suppose after the talk, if we have time, we can look at why this is true and give a proof. But this is a lower bound then. So if a graph G has a maximum clique size of omega G, then the tree width of G is more than omega G minus 1. So you have basically bounded it. So it's between omega G minus 1 and between n.
A tree should have tree width 0, right?
No. So
it's the tree.
Second. So if you take the tree itself, what will happen is that the edges won't be there in any of the nodes. You want the node to be such that the endpoints of every edge should be in some particular node.
Okay.
So I think what you're trying to say is, if this was a tree, then this tree itself is a tree decomposition of itself.
Yes.
Right? In that case, what will happen is, look at this edge. So what I want, the second property says that if this is an edge, then its endpoints should be present in the same node.
Oh, okay.
Right? So the second axiom says that if UV is an edge, then there is some node of that tree decomposition such that both U and V lie inside its bag.
Right,
So,
right, right.
so if there is at least one edge, then the bag size will be at least 2.
Correct. Okay.
Hence trees are of 3 with 1. Okay. Now this is the separator property. How did third property imply this? So the theorem is as follows. So suppose I pick any arbitrary node Z in the tree decomposition, and then it will divide the tree T into two parts. So let's say it's C1 and C2. Now what I'll do is I'll take the union of the vertices in the back of every node in C1. So whatever vertices are in this node, whatever vertices are in the back of this node, in the back of this node, I'll take the union over all of them over C1, and I'll remove whatever vertices are there in the back of Z. So I'll take the union of chi I over C1 and remove chi Z. Call this V1. Similarly, I'll do it for chi I minus chi Z. I'll do this for the second component and I'll call this V2. Now V1 and V2 are subsets of vertices of G. The separation, as per the separation property what we required, we need to prove that there is no edge which goes from V1 to V2. That is what we need to show. So how to prove this? So suppose that there was indeed an edge. So suppose there was, let's say there was some edge UV which went from V1 to V2. So you are able to see, right, what we are doing. So if this was the original graph G, then there is something here. This is your chi Z, and then it has divided into these two parts. So this is V1 here and this is V2 over here. Now we are assuming that, okay, suppose there is an edge which goes from here to here. Let's see, U is in V1 and V is in this side. Now, since this is an edge of the graph, I know that there is some node in this tree decomposition which will contain both U and V. Suppose I is that node. Without loss of generality, let it sit inside C1. Now U and V both are inside I, and I know that there is some node here. Let's say it's this node here which contains V. Right? This node contains V because we know that small v is in V2. So V lies here, which means that V lies on the path connecting them, because the subtree should be connected. This was the third property, right? So the third property said that look at all the nodes which contain the vertex V, then that should form a connected subtree. And so we know that V lies here, so we should lie on everywhere in between. And which means that V lies in Z also. So V lies in chi Z. This implies that V lies in chi Z. But if V lies in chi Z, then V can't belong to V2, and this is a contradiction. Hence the third property implies the separator property with respect to G. Fine. So we'll move to the next part. Now comes the actual part. So we are doing a tree decomposition. So we are doing a dynamic programming on a tree decomposition. So you see the point here, right? So the main problem that we have to look over here is that the dynamic programming is not being done on the actual graph. It is being done on a representative of the graph. And on this representative, there is no such property of, disjointness or something. Like nodes can be there in many vertices, the vertices of G can be there in many nodes of this tree decomposition, and well, it is somewhat complex in general. So doing a dynamic programming on a tree decomposition to get a result about the actual graph is something not very trivial. And this needs an approach that is different from the usual dynamic programming we do. So such an algorithm, this different sort of algorithm, was developed by Arnborg and Proskowski in, I guess, 1985, if I'm correct. And their algorithm was well, efficient but very difficult to understand. So then it was in 1997 that Bodlander came and simplified this algorithm for us, and that is what I am presenting to you. So this is what the algorithm looks like. But before we look at the algorithm, let's look at some other property of the tree decomposition. So in order to make our life easier, what we'll do is we'll define a tree decomposition to be a nice tree decomposition. If T is a rooted binary tree, and every node of this tree decomposition is either a leaf node, a separator node, or a join node. So leaf node is something which has no children. A separator node is something which has one child, and chi-z is a subset of a child, as in the bag of a separator node is a subset of its child's bag. And the join node has two children, z1 and z2, such that the bag of this join node is a union of the bags of z1 and z2. So I'll give you an example of this, so that you have some idea as to what these three are. Okay, so we'll try to construct a nice tree decomposition given a tree decomposition of this graph. Okay, so that is what we are trying to do here. So look at this. So this is your graph. Forget this GZ for the time being. So this is your graph, and this is a tree decomposition. Now I want to convert this into a nice tree decomposition. So how to do it? So let's start from here. Okay. So ABE is fine. That is not an issue. So ABE is a leaf node. So you can see that this is a leaf node, and I'll keep this as it is. So I'll keep ABE as it is. So I'll just place it here. Now from going to ABE to BCDE, there is a problem because BCDE is neither a separator node nor a join node. So what can we do? So first thing that we observe is that BCDE does not contain the vertex A. So the good idea would be to just simply drop A. So let's do that. So let's just drop A. So I started with ABE and I have dropped A, so I have got BE. And BE is a separator node. You can see why B is a separator node, because its bag B comma E is a subset of its child's bag A, B and E. So this is a separator node, fine. So okay, so now we have BE here, and we want to make this into a join node. So we already have BE, we want to make it a join node. So what are the two vertices left? The two vertices are C and D. So I'll just add them as a new leaf, or I'll add BCD as a new leaf, and then I'll combine them together and I'll get this join node. So I have leaf, separator, and this is a join node because BE union BCD is BCDE. Now what should the next step be? So look at BCDE, and the next vertex in this thing is CDE. So clearly I want to drop this B, so I no longer need a B, so I'll make another separator vertex and I'll just leave out B from this algorithm. Cool, so this is fine. Now let's look at the other branch. Let's look at DF and FG. So, well, FG is something I can. So FG has a problem. What is the problem of FG? The problem of FG is that DF here, so this contains D, but this is not a superset of this node. In order to make this node a superset of this node, I'll have to add D here. So I'll do that. So I'll do this DFG over here, and then I'll add a D here, and then you will keep DF as it is, and then you get this. So you have made CDE, you have made DF, so practically you have completed the entire tree decomposition. But for a nice tree decomposition, these are two still, different trees. So in order to join them, you simply have to add an extra join node and you're done. So this is a nice tree decomposition. So the blue ones here are join nodes. Why are they join nodes? You saw the definition, right? So it has two children, let's say this and this, and the union of its bag, that is CDEF, is the union of CDE and the union of DF. Likewise for BCDE. The red ones are separator nodes and the orange ones are loop nodes. So this is a nice tree decomposition for this graph. Okay. Is that fine? Fine.
Does this always maintain those properties?
Sorry?
Like if you made some changes to the original tree decomposition to get a nice tree decomposition. Does this always maintain those properties?
So in general, so Bodlander proved this. In general, if I give you any graph, then you can find a nice tree decomposition in linear time. I was just trying to give you some motivation as to how this is generally done.
Cool.
And there are proper algorithms to do this.
Oh, okay.
Right. Yeah. So this is what we saw, and we generated this nice tree decomposition. And given a tree decomposition, you can create a nice tree decomposition in linear time, specifically this thing, order of k into b of g. Now you define something called a terminal subgraph. What is a terminal subgraph? So you look at this tree decomposition, you pick any node, suppose this is Z, and you look at the subtree that is hanging from that node. And then you take the union of every single vertex present in the bags of these nodes. So A, B, C, D, E. This. So all these vertices in the original graph A, B, C, D, E will form the terminal node. So this subgraph of G is called the terminal subgraph of G with respect to the node Z. This is just a definition that we need. Now comes the actual part, the actual algorithm for solving the tree decomposition problem using dynamic programming. The idea is as follows. As a first step, what we'll do is we'll define, suppose there is a problem P that I want to solve. Now, how should I go about solving this problem using dynamic programming? The first step is to find out what a good solution would be. So first we define a general solution of P that I wish to attain. Now given this solution, so note that what you are going to ultimately do, you are going to travel your dynamic programming through the nodes of this tree. And if you are going to the nodes of this tree at every single point, so remember in the first algorithm, we were looking at the subtree sitting beside the subtree hanging from a vertex. So this is the same thing. The only point is that now we want the subtree hanging from that node represented as a subgraph of G, because G is where we want to do everything. We don't want to do everything in the tree decomposition. We want to find the properties of the graph G. And hence what we'll do is, for every node Z, you look at the terminal subgraph formed by Z. So you look at GZ, and you'll try to define a partial solution for GZ. Partial solution as in, suppose that I have a solution for the actual problem P, then what does this solution look like when I restrict it only to this terminal graph GZ? That is my second step. And then the third step would be, I have to find a relation between these two. So what is the relation between a partial solution and the actual solution of the problem? This we'll call an extension. So once we know, this is our problem, this is the solution that I want, this is a partial solution I'll expect at every step of the dynamic programming, and this is an extension, this is the property which tells me how the partial solution and how the actual solution are related. Once I have been told all this, we'll define something else, we'll define a characteristic. And this is where the most important difference lies. So for every solution, for every partial solution, so you are at a node Z of the tree. You are at a node Z of the tree and you have some possible partial solutions for the terminal graph GZ. These need not be one solution, like there can be many solutions. For each solution, you will define something called the characteristic. This characteristic will indeed help us at the end to determine whether our partial solution can get extended to an actual solution or not. So the property of extension we saw here, The question is, can we extend it? That we'll determine using this characteristic. So what is the property of a characteristic? So the property of a characteristic is that if two partial solutions have the same characteristic, then one is extendable to a solution if and only if the other can be extended. Or in other words, every single partial solution which has a particular characteristic should be able to be extended to the actual solution of the problem. Okay, so now what we have done is we have defined a solution. We have defined a partial solution for every node Z of our 3D composition, and we have looked at what all possible characteristics could be. Now there is obviously no one single partial solution, so there could be many partial solutions. So for each of these partial solutions, on the terminal graph GZ, you find out the full set of characteristics. As in, you make a set of all the characteristics of every single partial solution on GZ. So you take the graph GZ, you find the partial solution, find its characteristic, put it in the set. You do this for every single partial solution. And then you will get a set for GZ. This set is called the full set of characteristics. That is every possible characteristic of every possible partial solution on the terminal graph GZ. And now we'll do the dynamic programming using this full set of characteristics. So what we'll do, we'll reach to a node Z, and then we'll try to determine the full set of characteristics for that node Z using the children of Z. And we'll keep on doing this in the tree decomposition until we reach a root R. After we reach a root R, what we simply have to do is use this full set of characteristics of root R and connect this to the actual solution of the problem. Basically use it to solve the problem efficiently. Is it fine till now? Well, okay, I guess that's fine, so we'll continue. Good. So you see, in this entire process there are two important steps. One is finding a good characteristic, because the entire thing depends on characteristics. And the second step would be that you want to show that for every terminal node, the full set of characteristics is some polynomial of n. Well, if it is not a polynomial of n, then all our efforts are like wasted, right? Because, well, already it was NP hard. There was some exponential solution I could have found by taking all the possible subsets and blah blah blah. So why even bother doing dynamic programming if even dynamic programming turns out to be exponential? Hence, it is necessary that these full set of characteristics are polynomial in n. And this is a crucial property that has to be checked every time. So we look at the three colorability problem. So so this is the last part of this talk. So I have explained you how the dynamic programming works, and we'll practically try to, not practically, okay, I don't know what to say, but we'll see an example of how this method works for the particular problem of three colorability. So we saw initially that three colorability using dynamic programming on trees made no sense. So basically there was no way of using dynamic programming or for the three colorability problem on graphs in general. But using this tree decomposition, making the graph tree-like, we have found a method to use dynamic programming which will help us solve this problem in quite a polynomial time. I think it's order of n cube or something, but I'm not sure. So this is how we'll do this. So we'll go step by step according to the 6 steps. First, I'll tell you what the problem is. The problem is you are given a graph G, and you assume that G has a nice tree decomposition with a tree with K. And you want to check if G is indeed three colorable. So what is the solution to this problem? A solution to this problem would be a mapping S from the vertices of G to the numbers 1, 2 and 3. The numbers 1, 2 and 3 denote the color. So the first color, second color, third color, such that it satisfies the property whenever U and V are adjacent, that is UV is an edge their colors f of u and f of v should be distinct. So this is a solution to the problem that I am looking for. Well, what is the partial solution to the problem? So, uh, suppose if suppose the graph was three colorable and I color it using three colors, and then I look only at the terminal subgraph. I look at this subgraph gz of g. Then when will I say that this subgraph is three colorable? Well, this subgraph would be three colorable if again there is a mapping f dash from the vertices of this subgraph to 1 to 3 which satisfies the same property. That is obvious. So we have a solution, we have a partial solution. So what is the relationship between this solution and the partial solution? The relationship is actually quite simple. The relationship is simply that if f, the actual solution, were an extension of the partial solution f dash, then f, when restricted on this subgraph gz, should be equal to f dash. So basically this was the entire graph, and then now you have a smaller subgraph, and there is an f dash coloring that is happening on the smaller subgraph. There is an f coloring happening on the bigger subgraph, the actual graph. Then when I restrict this big f to this smaller graph, then what I should get is I should get back the function f dash. That is what the aim. Now let's define the characteristic. So the characteristic will be, so you are given this partial solution f dash, which is a mapping from v from the vertices of gz to 1 to 3, which satisfies those properties. Then the characteristic of f dash would be a restriction of this function to chi-z. Do you all remember what chi-z was? Okay, just go back there and tell you. So look at this graph. So this graph, so this is the subtree hanging here, and chi-z is basically this CDE. Okay, the bag associated with the node z is called chi-z. So chi-z is CDE, and the terminal subgraph is this entire thing. So CDE, this triangle here, is chi-z, and the remaining thing is the terminal graph associated with z. So right. So what is the characteristic? The characteristic is you restrict this function f dash on the vertex z. You'll restrict it to chi-z only. Chi-z is a subset of this. And why is this true? The reason this is true is that the coloring of chi-z is all that we require. Why does the coloring of chi-z suffice for us? Well, any guesses? So what I am claiming is that given a partial coloring of gz, in order to go to the next step of dynamic programming, all I need to store is the coloring of this chi-z. Why is this true? Well, any ideas? No idea. Hello. Fine. So basically the idea is the separator property. So suppose if you look at B, okay, so B is not there in chi-z, and what this means is that B is in V1, so there is no edge from B to this F and G, right? And if there is no edge from here to here, then the coloring of B does not affect the coloring of rest of the graph. So I really don't care about any vertex which is not present in chi-z. The only coloring that I am concerned about is the coloring of this chi-z here. Does that make sense? This is the importance of the separator property. The separator property is telling me that I can very easily ignore all the vertices of gz which are not there in chi-z. And hence chi-z serves as a very suitable characteristic for our function. So now that we have defined the characteristic, let's actually solve the dynamic programming. So the actual dynamic programming part. So note that the possible characteristic of partial solutions is simply a 3 coloring of chi-z. The size of chi-z would be at max k plus 1. Why? Because G is a k tree, and if it has a tree width of k, then the maximum number of vertices which are present in the bag of any node is equal to k plus 1. So chi-z will have at max k plus 1 many nodes. And so a 3 coloring of chi-z can be done in 3 power k plus 1 days. This thing is actually a constant. This is not even like, this is even better than the linear requirement. This does not even include n here. So this is actually a constant. So the full set of characteristics for any node is actually a constant. It could be less than equal to 3 power k plus 1, sure. But the point is, it is a constant, which was important for us. So how do we go about computing that? So look at the leaf node. So for the leaf node, the terminal subgraph gz is the same as chi-z, because there is no node under z, right? So since there is no node under z, the terminal subgraph gz and chi-z are the same graph. So f dash and the characteristic of f dash are indeed the same thing. Now suppose if I had a separator node. So I'll recall what a separator node was. So z is a separator node if it has a child z dash, such that chi-z lies completely inside chi-z dash. Okay. Since chi-z lies completely inside chi-z dash, and the best part is that you already have a 3 coloring of chi-z dash. So since you have a 3 coloring of chi-z dash, you automatically have a 3 coloring of chi-z. And so what this tells us is that if there is a characteristic mapping for f dash, then this characteristic mapping is also a characteristic for the node z. So, or in other words, the characteristic mapping lies in the full set of characteristics for the node z, if and only if it is also lying in the full set of characteristics for the node z dash. Right? Okay, so I think that's there. The last part that we have to look at is a join node, and join node is basically very simple. So for join node, what you have to do is, okay, join node you have z and it has two children a and b, and chi-z is a union of chi-a and chi-b. So I'll just, right, so basically now what we want to say is, suppose you have a characteristic for chi-a and you also have a characteristic for chi-b. What does that mean? That means you have a 3 coloring for chi-a, you have a 3 coloring for chi-b. And once you have the 3 colorings for both of them, how can you obtain a 3 coloring for chi-z? That is the question. To obtain the 3 coloring for chi-z, the first condition should be that the 3 colorings for chi-a and chi-b should match on their intersection. So I have rewritten the conditions here. And so first thing is that the 3 colorings should agree on the intersection of chi-a and chi-b. And second condition is that, suppose if I have a vertex u here and if I have a vertex v here and I join u to v, then it is possible that u and v have the same color. So I want to prevent that. So the next check that I want is that for every u in chi-a and v in chi-b, if uv is adjacent, then the coloring of u and the coloring of v are different. If these two properties are satisfied, then I can say that that particular coloring of chi-z is a characteristic for the join node z. Okay, Now using all this, you'll just keep on doing this every time, and at the end you'll reach the root. After you reach the root, how will you say whether a graph is three colorable or not? So that is pretty simple. Uh, so remember what happens at every node. So if I have reached node Z, what will happen is that the terminal subgraph GZ will have some good coloring which has already been given to it, right? So now when I reach the root R, and if it has at least one characteristic, right? So if it has at least one characteristic, that is, it has at least one three coloring of chi R, then this means that chi R can be three colored, and the rest of the entire graph can also be three colored, such that chi R and the rest of the graph don't contradict each other. And because of this, I can say that G is indeed three colored. So this is the dynamic programming algorithm. Since we are somewhat short of time, what we'll do is I'll quickly conclude this thing, and then we can have some side remarks and small examples and all. So say look at this first. Let's just have some concluding remarks. So dynamic programming on 3D compositions is pretty good, but still there are some tiny problems. So one important problem was you assumed here that the tree width of the graph G was K. Now given that the tree width of graph G is K, you can find a nice tree decomposition of G in linear time, and hence everything is good. But if this value were not known, then finding the tree width of a graph is actually an NP-complete problem. And because you are not able to find even the tree width of the graph in polynomial time, you can't find its tree decomposition, and this entire method becomes useless. You can't use this. So then, well, was all of this even useful? Because given a weird, complicated graph, the very first question would be as in, okay, I don't know its tree width, then what do I do? So, well, so in order to resolve this problem, you divide the graphs into certain classes. So you look at certain classes, suppose, so you look at chordal graphs, you look at complete graphs, you look at partial K-tree, series parallel graphs, etc. And for each of these classes, you can theoretically obtain the tree width of the graphs present inside those classes. And once you have done so, and let's say you encounter a very new graph, you see if that graph lies in any of these known classes, you will get the tree width, and once you get the tree width, you will do this entire thing in polynomial time. So well, you can't do it for every graph, but at least we have done something better than trees now. And you can actually solve the three color problem on some useful graph. So this was one thing. Another thing that I just wanted to mention was that you look at the join node above. So this join node, so defining the problem, defining the rules for this join node can sometimes be actually very difficult. In order to overcome this, what Bodlander did was he gave an alternate definition of a nice tree decomposition, where there are four types of nodes: a leaf, a forget node, introduce node, and join node. So forget node is something again which has one child, and as you go from the child to the parent, you are losing out one particular vertex. You are losing out only one vertex. As opposed to a separator node where you could lose out many vertices, a forget node loses one vertex. An introduce node does the opposite. It adds one vertex. And a join node is similar to the join node above. The only better thing here is that chi z1 and chi z2, the two children for z, are actually equal. So basically you are taking an equal set here and an equal set here, and then you are joining. So these properties actually help to simplify this 3D composition process. I think that's all from my side. Cool. So I think we can stop here. Is there any question in general? Fine, I'll at least stop the recording, that's all. Are there any questions, or else we can stop? I could actually, if you all have time for a few minutes, I could show how this algorithm works, the three color algorithm works for this graph if you're interested. Would that be fine, or do we want to wrap up?
Yeah, I don't mind.
Cool, so we'll look at this one. So, okay, so this is a graph that I have given, and I have already constructed a nice 3D composition. Now in hindsight, we know that this is not 3 colorable, but I'll just go with it for the sake of it to show how we'll be able to do it. So these two are leaves, this is a join, and this is a separator node. So by the time we reach here, we have actually tried out every single thing. And so I took the example. So let's start with BE. So BE is a single edge. So I want to find out all possible 3 colorings for BE, and that is actually simple to do. So if B has the color 1, then E will have a color 2, or it will have a color 3. Then I have 2 1, 2 3, and 3 1 and 3 2. So these are all the possible colorings for B and E. So the first number represents the color for B, the second number represents the color for E. I can do a similar thing for AE, and indeed AE will have the same step. So it will be 1 2, 2 1, 1 3, 3 1, and 2 3. So that is what happens for AE. And uh, now comes the join node, AEB. So for join node, what we need is that the first thing that we want to look is, okay, right. So the first thing that we want to see is that, uh, so this is okay. This is a join node. The first thing we want to see is that these colorings are matching on intersection. So what is the intersection of these two? The intersection of this and this is basically the set E. So let me fix something for E. So suppose E has been fixed with the color 1. So if E has been fixed the color 1, then A can have the color 1. A can have the color 2, or A can have the color 3. And B can have a color 2 or 3. So this is the first property. I fix the color 1, that is the intersection, and after fixing them, I look at whatever possible colorings are there, and I have 4 options. So the 4 options that I currently have are 2 1 2, 2 1 3, 3 1 2, and 3 1 3. Then I'll apply the second condition. The second condition is that if there is an edge from this set to this set, then its endpoints should have different colors. So let's look at the graph. So indeed A and B is an edge. So A is in one of the child and B is in the other child. So I would want A and B to have different colors. So basically 2 1 2 is not allowed and 3 1 3 is not allowed. So that gives me the 2 possible colorings when E is given the coloring 1. So using this I can write down the remaining possibilities, that is 2 3 1. So these are all the possible characteristics for the coloring of node Z. Now let's go to this node AB. So for a separator node, all you had to do was you have to just remove this beach wala thing. As in you just have to take a restriction. And then if you take a restriction, then what is it that you'll get? So let's just take a restriction. So 2 1 3 may say I'll remove 1, so I'll get 2 3, 3 2, 1 3, 3 1, 1 2, and 2. So this is whatever is there for AB. And then I'll do this for CD. So for CD I'll get the same set actually, 1 2 2 1 2 3 3 2 3 1 1 3. And now using this, I would like to construct the characteristic for ABCD. So to construct the characteristic for ABCD, these two are disjoint. So in the join wala part, the first point is nothing to be checked there. So all you have to check is that if there is an edge from AB, A or B to C or D, then its endpoints should have different colors. And then ultimately using pigeonhole or using programming or whatever, you can see that there is nothing such possible. So for example, suppose if I had given, if I had taken the first one, so AB was given 2, 3 and CD was given 1, 2. Now I know that A and D are connected because this is actually a K4. A, B, C, D is a K4. A and D are connected. And as a result of this, 2 and 2 cannot be the same. So this one has to be removed. And in this way, if I enumerate all the 36 possibilities, each of them will have to get eliminated because there is an edge going from AB to CD such that their colorings are the same. And so you'll find this to be the empty set. And because the root is an empty set, you will conclude that there is no three coloring possible. So that is how this algorithm works. Right. So that is all from my side.